Hello everyone, welcome to Signal Systems and Signal Processing with Wolfram U. The topic of this lesson is elementary signal operations. Let's begin with a quick overview. This lesson covers elementary signal operations. We are going to look at the effect of these operations on signal characteristics. We will do this in continuous time as well as discrete time. Consider this sinusoidal signal x of t, which is defined as indicated here. In the definition of x of t, we have two variables, the variable t, which is called the independent variable, as it can take any value within the domain of the function x of t. Here it can go from minus infinity to positive infinity, for example. And the variable x, which is called the dependent variable, since it can change according to the rule of the function depending on the value of t. The two basic operations that we will look at are scalar addition used for shifting the signal and scalar multiplication, which we use to scale the signal. With this introduction, let's look at the first operation, amplitude scaling. Given a signal x of t, we want to see what happens if we multiply x of t by a constant value a. Let's consider this signal x of t defined as the piecewise signal that is shown here. The plot of the signal shows how the signal changes over time. If we multiply this signal now by 2, in the algebraic expression for the new signal, every element in the piecewise function has been multiplied by 2. And if you plot this signal together with x of t and 2x of t for comparison, we can see that starting with the blue signal x of t and going to the new signal, the orange one, the amplitude of the signal has increased. This is an example of what we call signal magnification. The range of the new function is doubled. Using this object, we can see how a times x of t changes compared to x of t for different values of the scaling parameter a. Starting with a equal to 1, obviously the signal has not changed when you multiply it by 1. If we increase the value of a, we get signal magnification. The amplitude of the signal gets larger. If we go to the other direction and look at the signal for positive values of a which are less than 1, we get signal reduction. The range of the new signal is smaller. And if we go to the negative direction, we have the same effects, but on the opposite side of the x-axis. The signal is also flipped vertically. For a equal to -1, we have signal negation. The second operation is level shifting. Starting with the signal x of t, we want to see what happens if we add a constant scalar a to x of t. Let's use this object to see what the change looks like for different values of the shifting parameter a. Starting with a equal to 0, as we increase the value of a, the signal is shifted up. The level of the signal is increasing. And for the negative values of a, the signal is shifted down vertically. The level of the signal decreases. For our first example, consider this signal transition applied on x of t, given the same piecewise function for x of t. We want to find the new signal after applying this operation, which is basically a combination of both amplitude scaling and level shifting. Given x of t, when we apply the operation, we will get this new signal. If you were to apply this operation by hand, you would multiply the signal by 2 and then subtract 3/2 from it, and you would do this for every element in the piecewise signal. The result will be as shown here, which is the same result as we got using the Wolfram language. For this transition, we went from x of t, which is shown here, and multiply x of t by 2, which caused the amplitude of the signal to increase. We had signal magnification. And then when we subtracted 3/2, the level of the signal decreased. The signal shifted down vertically. These operations in discrete time are applied in the same way. Let's look at an example. Given a sequence x of n, which is defined for integer values of n, we want to see how x of n changes when it is transformed to a times x of n plus b for changing values of a and b. Let the sequence x of n be the image shown here. So far, we have worked with signals where we were given the algebraic expression of the signal or the graph of the signal. An image is also a very good example of a signal. For images, the value of the signal represents the brightness of the image as a function of horizontal and vertical spatial variables, a function of the position in the image, instead of time, as we have had it so far for the independent variable. Using the Wolfram language, you can apply these operations directly on the image, which is what we have for this manipulate expression. Changing a, the scaling parameter, as we increase the value of a, the range of the function increases. And this shows as an increase in the contrast of the image. If we decrease a, the contrast decreases. And changing the value of the shifting parameter b shifts the level of brightness everywhere for all values of n by a constant value b. Increasing or decreasing b increases or decreases the brightness. So far we applied these operations on the independent variable x. Next, we will see the effect of scaling and shifting on the independent variable t. When time is scaling, we multiply the independent variable t by a constant scalar a and transform the signal x of t to x of a times t. Plotting the old signal and the new signal, starting with a equal to 1. If we increase the value of a for values which are greater than 1, the signal gets compressed horizontally. This is what we call time compression. And when the value of a is positive and less than 1, you can see that the signal is expanded horizontally. This is called time expansion. If a is equal to -1, the signal gets flipped horizontally through the vertical axis, and the signal is referred to as, this operation is referred to as time reversal. Time shifting is when we are adding a shifting parameter a to the independent variable t. So instead of x of t, we will have x of t plus a. As we change the value of a for negative values of a, the signal gets shifted to the right horizontally, and basically the signal occurs at a later time. We call this time delay. And when the value of a is positive, the signal is shifted to the left. This is what we call time advance, as the signal is occurring at an earlier time. For the second example, consider this operation, which is basically again a combination of two operations. First, one is subtracted from t, time shifting. The signal will be shifted to the right, and then multiplication by 1/2, time scaling. Since 1/2 is less than 1, the signal is expected to expand in time. We want to see the effect of this operation on x of t, which is defined using this piecewise function. Plot of the signal shows that it looks like a triangle signal. Using the Wolfram language, a new signal can be obtained as expressed here. And again, if we were to do this by hand, we would replace t with t minus 1 divided by 2 and simplify, and we will end up with the same result as we got using the Wolfram language. Plotting these two signals together, you can see that as expected, the function has shifted to the right and also expanded in time. Let's look at a different kind of example. Assume that we have the original signal x of t as shown here on the left side, and we want to change this signal to what is shown on the right-hand side. We call this new signal y of t. The question is, can we design a system that takes x of t and returns y of t? What operations do we need to apply on x of t to get to y of t? As you can see, the signal has shifted horizontally. This translates to time shifting. And also, there is time compression or time scaling. Therefore, the transformation should be in time domain, and y of t should be of the form x of a times t plus b for some values of a and b. To find the values of a and b, looking closely at the two signals, and if you compare the red dots in the original signal and the new signal, and compare the blue dots, you can see that the red dot at t equal to -2 corresponds to the red dot at t equal to 1/2 in the new signal. And t equal to 2 in the old signal corresponds to t equal to -3/2 in the new signal. Therefore, with this transformation, matching the red points, we get one equation as indicated here. and the transformation of the blue point gives the second equation. Therefore, we have a set of two equations that we can solve for the two unknowns A and B. Once we have A and B, the signal transformation can be written as x of minus 2t minus 1. Now, if we get the expression for the original graph, which was on the left-hand side, as shown here with this piecewise expression, we can solve for the new signal by applying the transformation that we found. And if we plot this new signal, you can see that it is the exact signal that we were looking for. In discrete time, applying these operations on the independent variable is limited to using integer values for the scaling parameter and the shifting parameter. For time shifting, we can shift the signal horizontally by an integer value, and in time scaling, we can multiply the independent variable by an integer value. The operation is called downsampling. And when we can also divide the independent variable n by a positive integer value k, when n is visible by k, and it will insert 0 for other values of n. This operation is called upsampling. Given a sequence x of n, when applying downsampling, we are basically keeping every kth sample of the sequence and discarding the rest of the samples in the sequence. That is, the new signal y of n is the value of the sequence x at 0k, 2k, and so on. We are skipping samples and jump forward faster. This will cause time compression in the sequence, and it will compress the signal horizontally, as shown for this signal. On the left-hand side, we have x of n, where we take samples at red points to get to y of n, as shown on the right-hand side. This sequence was taken from the data of the image of the two foxes that we saw in previous examples. Let's see the effect of downsampling on the image at the same time. Downsampling reduces the dimensions of the image. If we look at the two images with magnification 1, the size of the image is reduced in space. Downsampling is used when transmitting images or when we are interested in saving storage space. With upsampling, every sample is transformed to k samples. We insert k minus 1 zeros and then the sample itself, or we insert k minus 1 zeros between samples of the original signal. For k equal to 2, for example, the new signal will be x of n with 1 zero added every 2 samples, as shown here. Another good example of signals are audio signals. An audio recording gives the measurements of air pressure as a function of time. For example, here is the audio recording of Neil Armstrong on the Apollo 11 mission.
That's one small step for man, one giant leap for mankind.
Now, applying downsample, keeping every second sample, and discarding the rest, causes time compression, as you can hear in this audio. And this is the result of applying upsampling on the original audio by a factor of 2. This time we added a 0 between samples instead of discarding samples, and so the sequence expanded over time. If we downsample this audio, which was already upsampled by a factor of 2, we get the original signal back, since we will remove the zeros that we had added.
That's one small step for man, one giant leap for mankind.
However, if we downsample first and lose some samples and upsample to add zeros in between samples, we don't get the same signal back. The time duration of the audio signal will be the same as the original signal. There won't be time expansion or time compression, but the audio will be of lower quality.
That's one small step for man, one giant leap for mankind.
In this lesson, we studied basic signal operations of shifting and scaling as they were applied to the independent variable and dependent variable in both continuous time and discrete time, as listed here. We saw several examples and also learned some new vocabulary related to signal operations, namely expansion, compression, time reversal, downsampling, and upsampling.